Hello, everyone. We're back for a new chapter. This one's going to be chapter 6 entitled Bones and Skeletal Tissue. Chapter 6 is a really introduction into us starting to learn some characteristics about bones and eventually leading all the way up to naming the most common bones that we have in the human body. But before we get to all that fun, let's start talking a little bit about the origin of our skeleton. And in order to do that, I want to remind you that the human skeleton initially is actually composed of cartilage, which is then later replaced by bone. It's very important to point out that the cartilage does not become bone, but it's replaced by bone. So part of what chapter 6 will tackle are some characteristics of cartilage versus bone, and of course the whole process that the bones have to go through to transition from one into the next, or I should say it better, to be replaced from one form to the next. Alrighty, so just a few common facts. Skeletal cartilage is composed initially of a very resilient molded cartilage. And this cartilage doesn't have any blood vessels, nor does it have any nerves. Instead, it will get the nutrients from what we call the perichondrium, which is best described as dense, irregular tissue that will surround the cartilage as a protective shield. This cartilage will then, sorry, my apologies, the perichondrium, in addition to providing the cartilage with blood vessels for nutrient, will also control the overall shape of the cartilage, preventing it from molding in an asymmetrical type version. Now, remind yourself that based on our histology conversations, that when you take a look at cartilage, it's composed of chondrocytes, and these chondrocytes will build upon the extracellular matrix, which is the backbone or the content of the cartilage. And as the chondrocytes build, eventually they become stuck in a little dip, in a little cavity, and that is called the lacunae. Now, speaking of cartilages, there are three types of cartilages. As you may recall, we have our hyaline cartilage, which is the most abundant. It is filled with collagen fibers, which allows it to become very flexible, very resilient, very absorbent to any type of pressure or stress. We have our elastic cartilage, which, as the name indicates, is full of elastic fibers, which gives us stretch and flexibility. And then we have our fibrocartilage, which is best known for enduring a lot of pressure and resistance being placed on it. So I like how it says it has the great tensile strength, and that is because it is filled with very thick collagen fibers. Now, if you bear with me for 1 second, I'm going to switch over to our next so we can take a look at this beautiful image right here of the human skeleton. And if we take a look at the color codes of blue, green, and red, we can see our different cartilages and what roles they play within the human body. So starting with the hyaline cartilage, you can see that you can find it within the composition of the sternum, connecting the breastbone over to the individual ribs. We have our articular cartilage over there. I'm sorry, our costal cartilage there. We have the cartilage that we find within the nose. And as you can see right here, you have your articular cartilages that are associated with the joints that will hold together the arms, the fingers, as well as over here by our hip joints. In green, we're going to have a little bit more flexibility. And oh, here you go. It is on what we call the pinna of the ear, which is the outer lobe of the ear, that you can freely fold over and it'll pop right back into shape. You will also find some elastic cartilage in the epiglottis, which is a fold of tissue that basically closes off the trachea anytime you swallow food so that the food goes behind it into the esophagus and not into the trachea, which would lead it to the lungs. In red, we have fibrocartilage. And you know what? I have to erase some of my markings so that we can see it a little bit better. But we could see our fibrocartilage in areas that are exposed to high amount of stress. So for instance, right here in the pubic symphysis, which is connecting the two hip bones, you will also see it within the articular cartilage of the kneecap by the meniscus. And then probably the most obvious one is right here between the vertebrae, protecting those bones and the spinal cord in our back. Now, next slide will discuss growth of cartilage, and it basically states that when you look at the trend line, there are two ways that cartilage can grow. One will be from the outside onward, and one will be from the inside. If you see that cartilage cells starts being secreted onto the perichondrium, which remember is that girdle, that protected chamber around it, and the cartilage cells are growing against the external face of existing cartilage, basically from the outside out, we call that appositional growth. Interstitial growth means within, inside. So now we're looking at the chondrocytes housed within their lacuna that are dividing and secreting new matrix, allowing for the cartilage to expand from internal to outwards. Calcification of cartilage is going to assist in the overall hardening of the cartilage, which will give it some of its resilience and some of its strength. But please keep in mind that calcification of cartilage does not indicate the formation of bone. It is two separate processes, and as I mentioned to you before, cartilage will be our initial source of the skeletal, which will then be replaced, not transitioned into bone. There are many different functions for our bones as we start to transition to some of their characteristics. I think looking at the list, none of these should be a surprise. So for instance, the bones will provide excellent support for the body and our different organ systems, protection, such as items like our brain, for instance, our cranium, our skull bones, surround our brain and protect it from external and internal features. Our spinal cord is encased by the vertebra bones, and of course, vital organs, such as, for instance, in our thoracic cavity, how we have our rib cages that will protect our lungs and our heart. They also provide excellent levers for muscle attachment, so movement will come into play. We also see that due to their calcium and phosphorus reservoirs, they can act as a mineral and growth factor storage, as well as the fact of it being able to house red bone marrow. It will allow for hemopoiesis, which is the formation of blood cells. Now you have red bone marrow and you have yellow bone marrow. Yellow bone marrow is actually composed mostly of adipose tissue. So this allows for fat storage within the bones as well, which is an excellent way of harboring extra energy sources for later use. And last but not least on our list, number 7, it says one of the functions of bones is hormone production, and that is due to the production of osteocalcin. And that particular hormone, which is secreted by bones, has many different functions, but its main goal is to help you regulate your metabolism and glucose levels by assisting in regulating insulin secretion. Physical attribute, we can go ahead and classify bones based on their overall shape. So over here we have an example of where the bones are classified either as a long bone, a short bone, a flat bone, or an irregular bone. A long bone, such as for instance the humerus, the ulna and the radius, the femur, the tibia and the fibula, these are all examples of elongated structures. You also have bones that are more on the short side, more of a Q type shape. So then we can, instance, for take a look at our carpals and the tarsals, which are the individual bones that make up our wrist and our ankle. We also have flat bones, such as the sternum has right here, our little breastbone, as well as with the bones that make up the skull. Those are all examples of flat bones. And last but not least, if the bone is not long, not short, and not flat, well, then it must be irregular. And an irregular bone means that it has a very unique shape, such as this lumbar vertebra right here. Another example would be, for instance, the sphenoid bone, which you find within the brain. Any type of bone that is not long, flat, or short, and has somewhat of a unique shape, we can go ahead and classify as an irregular bone. Now, bones, as we will be discussing them, and eventually we'll get to naming them, please keep in mind that the bones that we're going to be doing this way are a collection of different tissue types. So therefore, a bone is considered an organ. The most dominant tissue type in the bone will be osseous tissue or bone tissue, but you're also going to see that it will work very closely with things like connective tissue, muscle cells, nervous tissue, as well as with the cartilage. Now, to understand the bone structure a little bit better, we're going to go ahead and take a look at it from a growth perspective, a microscopic perspective, and of course, a chemical composition perspective. So let's start off with the growth anatomy, which is take a look at your bone. Oftentimes, you can distinguish it between a compact bone and a spongy bone. A compact bone means that whenever you look at the bone, it is homogeneous in its overall texture and color. It appears smooth and solid. Spongy bone is going to look almost like the sponge that you have sitting most likely on your kitchen counter sink or by the kitchen sink, my apologies. It's going to be full of little cavities. I actually like the description in the PowerPoint. It says it's made of a honeycomb of small needle-like or flat pieces. And what we do is we call these extensions, these little pieces of bone, we call them trabecula. And please bear with me. I'm going to show you some pictures to allow you to compare the compact bone versus the spongy bone. Now, the relationship or the organization between compact bone and spongy bone will differ, ultimately depending on the overall structure of the bone. For instance, if you're looking at what we like to call flat bones, we see that it almost forms what we call a sandwich, or better yet, a diplo. And a diplo basically states that you will have a thin area of spongy bone that will be covered on top and bottom by a plate of compact bone. And what we see happening is that compact bone will have a connective tissue membrane that will wrap itself around. It will have what we call the periosteum covering it on the outside, and then the endosteum will cover it on the inside. So once again, if you see the term periosteum and endosteum, please remind yourself that this is a connective tissue membrane that covers the compact bone, periosteum from the outside, endosteum from the inside. Now, in a little bit, I'm going to show you that not all of the bones will use periosteum and endosteum, and that is because the part of the bone that's usually associated with the joint that makes a lot of connection point, high levels of friction as one bone kind of rubs on the other, that will be covered by hyaline cartilage instead of the connective tissue membrane mentioned before. Let's take a look at some images to kind of bring these key terms to life. First off, here's our example of diplo. And diplo, once again, is when you create a sandwich where you have the spongy bone. You can see right here with the cavities. Better yet, let's follow our blue arrow and take a look at the trabecula, the bone formations as they form. And all these little openings that you have in the spongy bone, they can be filled with red bone marrow. And as you come back to the top picture, you notice that you have a solid layer of bone that sits on top and the bottom, and that is your example of compact bone. So anytime you see the term diplo, that basically means that you have a sandwich with the spongy bone in the middle and the compact bone covering it on the outside as well as on the inside. Now, a long bone, such as the humerus or the femur, will have a different composition. It won't have that sandwich format. Instead, it will have what we call a diaphysis, which is the tube section, and it will have an epiphysis, which are the end parts. Now, the tube section of the bone, the diaphysis, that is where you're going to see some familiar terminology, aka the periosteum and the endosteum. That is the connective tissue membrane that we were previously mentioning that will wrap itself around the compact bone in the shaft or the diaphysis section. Inside of the shaft is usually a cavity. We call it a medullary cavity. And this cavity can either be filled with red marrow or yellow marrow. In adults, it's often filled with yellow marrow. The end part is going to be called the epiphysis, and this is going to be the part that makes contact with other bones. So this will be covered with hyaline or articular cartilage instead of the membranes mentioned above. As we take a look at our picture, I'm also going to highlight what we call an epiphyseal line. The epiphyseal line is called the growth line, or you might have heard of the epiphyseal plate, which is known as the growth plate. The epiphyseal line is what we call it when the bone is actively growing. This is the initial point where the cartilage will form and be eventually replaced by bone. And then once you stop growing, that line, the epiphyseal line, will close off, and what's left behind is called an epiphyseal plate. So it's kind of like a little scar, a little remnant of the area of growth that you were seeing during childhood. Let's take a look. So here we have a humerus, and as you can see, it is a long bone. Notice how they've sectioned off the shaft of the bone and highlighted it as the diaphysis. And then they said for you on the side right here that you have the periosteum membrane that covers it on the outside. You can see this little blue U right here. And on the inside, you could see the medullary cavity. We can also call it the bone marrow cavity. And that one is lined by the endosteum. So the periosteum and the endosteum are your connective tissue membranes that cover the shaft or the diaphysis of the bone. The outer edges are the epiphysis, and as you can see, those will be covered by articular cartilage due to the fact that that's where the joints will be occurring and more friction. So the membrane won't really be as useful, but articular cartilage will be. I also want to point out that within the long bone itself, you can see the sections of spongy bone versus compact bone. And then they also went ahead, and let me just kind of erase some of these markings that I made right here. They also went ahead and marked for you the epiphyseal line, which is this particular line right here. And that, of course, as I said to you, is the area of active growth where the cartilage will duplicate and expand from as the bone is actively growing. And when the epiphyseal line closes up, we then call it an when the epiphyseal plate closes off, we then call it an epiphyseal line. So that is the difference between one and the other. All right, here is another of the interaction of your compact bone and the spongy bone. Here is your compact bone, and some of you might be seeing the ever familiar tree trunk rings, the osteons, which of course are the functioning unit of our compact bone. We've studied that before in our histology. And then here, the area with all these open cavities, that is the spongy bone. Spongy bone does not have osteons. Instead, it will have a very unorganized pattern of collection of the osteocytes of the bone cells, and then embedded within the cavities, you can see the blood vessels running through. Whereas in compact bone, the blood vessels are exclusively found within the central canal or the Hofversion canal of the osteon. Just a little bit more knowledge about those connective tissue membranes. This highlights the fact that the periosteum, which once again is found on the external surfaces of the shaft of the compact bone, is composed of a double layered membrane. We have the fibrous layer, which is the outer layer. This one is full of dense, irregular connective tissue. It will allow it to secure itself to the bone matrix by what we call Sharpie's fibers. And then the inner layer is the osteogenic layer. And the osteogenic layer, as the name indicates, means that there are lots of osteogenic stem cells that are found within this layer that can eventually give rise to all the different bone cells that are needed for bone growth as well as bone maintenance. You will also have connections to the nerve fibers and the blood vessels within the periosteum. And this membrane, in addition to providing protection, is also an excellent anchoring point for different tendons as well as ligaments. The endosteum is going to be on the inside by the cavity, and over here it tells you that it's composed of connective tissue as well that is slightly more delicate than the periosteum. It will come into contact with some of the trabecula of the spongy bone, and it will also have access to osteogenic cells that can differ in a wide array of different bone cells. Please keep in mind that your bone is an organ, so you will have continuous growth and or maintenance of it, and the periosteum and the endosteum help regulate or monitor how much stress is being placed on the bone, so it can determine the thickness and the overall growth rate of that particular bone. Inside of the cavity, the medullary cavity, in the diaphysis or the shaft of the long bone, I mentioned to you before that you can have red marrow and you can have yellow marrow. Red marrow is found in addition to the cavities also within the spongy bone openings and the diplo of the flat bones. In newborns, you will find it in the medullary cavity and all spongy bones. In adults, the red marrow will only be located within the heads of the femur and the humerus, and the most active regions will be in the flat bone of the diplo as well as some irregular bone, like your oscoccyx bone, which is your hip bone. Now, the remainder of the areas will replace their red marrow with yellow matter, which, as I mentioned before, is adipose tissue, and that is there as an energy resource. And if ever need be, like for instance, in the case of severe anemia, the yellow marrow can be converted back to red marrow. I would also like to show you table 6.1. This table highlights what we call bone markings. And for those of you who haven't really had a lot of exposure to bones and their overall naming, I think this table is worth a look at because it talks about the fact that certain terminology will always indicate a particular appearance or characteristics of the bone. So for instance, it says if you see something that has a tuberosity in its overall name, what that means, like for instance, the ischial tuberosity, that means that you're looking at a large rounded projection. If you're looking for a epicondyle, that is a raised area on or above the condyle. A spine is usually sharp and slender and pointed. And as you can see from the illustration, it will give you some examples. There's no need to memorize the name of the bone marking and the description. It's just a really nice way to kind of read through it and start looking for these key terms as we starting to name the process. Like for instance, anything that has the term foramen, that means that there's a large opening that we're looking for. A meatus is a channel or a passageway. So for instance, if I say to you that you have an acoustic auditory meatus, that is fancy for saying your ear canal, because a meatus is a tunnel or a passageway. A fossa is a shallow depression, and a sinus is a cavity within a bone. So please take a few minutes out, take a look at table 6.1. And like I said, you don't have to memorize these, but it is a really nice way to start seeing some of the terminology or the markings, which will make it easier for you to identify the bones once we start looking at them in our next chapter. The final part of this particular lecture I want to talk about is the microscopic anatomy of bone, aka the different cell types that you would come across in the bone tissue. And there are 5 major cell types to mention. We have our osteogenic cells, osteoblast, osteocyte, and bone lining cells. And these 4 are going to be clustered together because they're going to come from the same stem cell origin, aka the osteogenic cells. And then we have our osteoclast cells, which will have an entirely different origin and an entirely different function. So here it says your osteogenic cells are going to be a version of stem cells that you find within the periosteum and the endosteum, and these are continuously dividing through mitosis. And once properly stimulated, this stem cell, this osteogenic cell, will become an osteoblast cell. B is for building, so this is going to be a young cell that's actively building the matrix of the bone. So as you can see on your PowerPoint, it says bone-forming cells that secretes an unmineralized bone matrix called the osteoid. So it hasn't been hardened yet, but it's secreting the extracellular matrix. Once the osteoblasts are done growing, remember they're going to get stuck in their little lacunae. At that point, we're going to call them osteocytes. So the osteogenic cells, which were our stem cells, became our osteoblast cells, which will then eventually become our osteocyte, which is a mature bone cell that is stuck in the lacunae and is no longer dividing. It still, however, plays an extremely important role because it will regulate how much stress and tension is being placed on the bone, so it can assist with the remodeling of the bone, which will continue throughout the entire lifetime. Helping the osteocyte are the bone lining cells. These bone lining cells can be found on the external bone surface, where they're also called the periosteal cells, and internal surface, where they're called the endosteal cells. Okay, so the bone lining cells, they will help maintain the matrix and assist the osteocyte in this particular function. So osteogenic, osteoblast, osteocyte, and bone lining cells. And then our fifth cell are osteoclasts. Osteoclast cells are all about destroying or breaking down the bone. They come from a hemopoietic stem cell that also gives rise to macrophages. Osteoclast cells are extremely large cells that will assist in what they call bone resorption, which means the breakdown of the bone matrix. And what we see, it's going to do so by utilizing its ruffled border that it has at this end, which increases the surface area that the osteoclast has contact with, and it will go ahead and secrete an acidic type of solution that will literally start breaking down and melting down the hardened matrix of the bone. So your osteoblast cell will build, and then your osteoclast cell will destroy. And part of maintenance of the bones is regulating the action of these two so that you can produce bones that are strong and healthy. All right, I'm going to stop right here for part 1. If you have any questions, comments, or concern, please do let me know. And I hope to see you soon for the second part of our Chapter 6 discussion. Bye, everyone.